Welcome back to the deep dive. We've all seen AI write code, craft pretty compelling marketing copy, or, generate stunning images. But there is one challenge that really separates the good models from the genuinely great ones. Can a large language model actually predict the future?
Well, that is the ultimate test of generalized intelligence, isn't it? Of true inference. We know these models like GPT-5, Claude 3.7 Sonnet, and DeepSeek R1, they excel at recalling or restructuring knowledge they were trained on, but forecasting real-world dynamic events that haven't happened yet, social, political, economic, that requires something else.
It requires actual synthesis.
Exactly. Synthesis, understanding momentum, assessing complex risks. And the loss folk research we're diving into today asks this really critical fundamental question. How uneven is an LLM's forecasting competence across different domains?
And that defines our mission for today. We're analyzing the results of this incredibly rigorous study, which focused entirely on predictions for events that occurred beyond the model's training cutoff dates.
So they were forced to reason about the truly unknown.
Absolutely. And here's the core conflict we need to understand. We are unpacking how performance fundamentally changes when you, the user, augment the prompt and give the model factual, real-time news context.
Which is what we all do.
It is. Okay, let's unpack this right away, because the common assumption, and frankly, my immediate intuition, says that more context should always improve our prediction.
You think so. It just makes sense.
It makes total sense. If I'm trying to forecast political unrest or a specific stock movement, giving the AI the latest headlines should make its prediction sharper, right? It should refine the signal.
It absolutely should, intuitively. But the research shows that sometimes adding recent factual news context actually makes the model's prediction substantially worse.
Worse. Not just it doesn't help, but it actively hurts.
Actively hurts.
Hey.
It degrades accuracy, and critically, it damages calibration. It's the difference between adding pure signal and introducing dangerous, misleading noise. And for LLMs, that noise can sometimes activate these deep, systematic vulnerabilities.
Okay, so before we get to the results, we have to appreciate the rigor of the methodology here, because this wasn't just a simple test.
Not at all.
They had to ensure the models were truly forecasting events outside their knowledge window.
That's right. The integrity of the results rests entirely on the quality of the benchmark. They started by collecting a massive pool of approximately 10,000 forecasting questions.
Wow.
And crucially, these weren't internal, made-up questions. They were drawn directly from real-world prediction markets. Sources like Polymarket, Metaculus, and Manifold markets.
So that guarantees they were real high-stakes bets that people were actively trying to resolve.
Exactly. And the time window was essential. The questions covered events spanning from January to July of 2025. This guaranteed that the models, even the cutting-edge ones like GPT-5, were forced to reason about a future they hadn't been trained on.
Okay, but 10,000 questions sounds like an enormous, messy data set. I mean, it must be full of noise. How much work went into filtering that down?
A lot of work. They needed to distill that raw volume down to a high-quality, curated set of just 392 meaningful items. And they used this really disciplined three-stage pipeline to do it.
Take us through that filtering process, because I think that shows the level of scrutiny they applied.
Okay, so first was volume filtering. They removed questions from low-liquidity markets. These are usually hyper-personalized or non-forecasting questions.
Like what?
Think of questions like, will my friend Bob win his local chili cook-off next month? We want public, verifiable events, not, niche personal bets. Removing that noise was essential for any kind of statistical relevance.
Understood. Get rid of the trivia. What was the second step?
The second was classification. This is where they used an LLM as a judge, specifically Gemini 2.5 Flash, to sort the remaining questions into 6 primary categories.
So politics, entertainment, sports, that kind of thing.
Exactly. Politics, entertainment, sports, technology, finance, and geopolitics. And this established the domains they would use for comparison.
Wait, so they used AI to categorize the data that they would then use to test other AIs. That's clever.
It is, provided the categorization itself is robust. And then finally, they conducted one last filter to remove any residual localized or non-event-based questions, leaving that final balanced benchmark of 392 questions across those 6 key domains.
So they ended up with a high-stakes, balanced benchmark. Now, when they evaluated the results, it wasn't just about simple accuracy. You mentioned calibration. They focused on probabilistic competence.
Right.
Can you walk us through the metrics they used to measure success?
They relied on 3 key metrics. First, accuracy, which is just simple correctness. Did the model's predicted resolution yes or no? match the actual outcome.
Straightforward enough.
But for forecasting, the other two are far more critical. They use the Breyer score and the expected calibration error, or ECE.
The Breyer score, what does that measure?
So the Breyer score is a standard for evaluating probabilistic forecasts. It penalizes predictions based on both how wrong they were and how confident they were when they were wrong. It's the mean squared difference between the predicted probability and the actual outcome.
Okay. And ECE, that's where the rubber really meets the road for understanding AI behavior, right?
Absolutely. Calibration measures how well the model's stated confidence matches its actual correctness rate. Think of it like a professional weather forecaster.
Right.
If that meteorologist tells you there's a 90% chance of rain, that prediction should be right about 90% of the time over the long run. If they say 90% chance, but it only rains 40% of the time, their calibration is terrible.
Even if they occasionally get the yes or no answer right.
Right. A high ECE means the model is either wildly overconfident in its bad predictions or overly cautious in its correct ones. It tells us the model doesn't truly understand the boundaries of its own knowledge.
Or in other words, it tells you whether you can actually trust the probability score the model gives you.
Precisely.
Okay, that sets the stage perfectly. Let's look at the baseline performance. The model's relying only on their foundational training, their ability to reason abstractly. What did the models look like before they were given any of that external news context?
The primary takeaway from the baseline test is pretty profound. LLM forecasting ability is highly uneven across domains. It's conditional, you see clear domain expertise and, well, clear blind spots.
So give me the high achievers. Which domains did they just nail?
Geopolitics and politics showed remarkable strength right out of the gate. In geopolitics, models consistently achieved high accuracy. GPT 4.1 hit an impressive 88% accuracy. They also show strong calibration in these areas, especially GPT-5 and Claude 3.7.
Hold on, that seems deeply counterintuitive. Geopolitics involves massive uncertainty, shifting alliances, state secrets. Why would an LLM be better at predicting the outcome of an international treaty than, say, a stock price move in finance?
And that's the key insight. What's fascinating here is how well the models handle highly structured domains, even if they're complex.
Structured. Geopolitics feels like chaos theory sometimes.
But it's a structured chaos. Despite the uncertainty, it often relies on synthesizing established political principles, institutional procedures, policy precedents, and things like institutional lag.
Ah, how long it takes a government to actually implement a major decision.
Right. The models are adept at chaining together these logical, rule-based steps based on their vast pre-training data. It's pattern matching based on historical state behavior and economic principles.
So it's not about predicting a specific person's whim, but predicting the predictable momentum of large, slow-moving institutions.
Exactly.
Okay, so on the flip side, where did they struggle the most? Where did they look like novices?
The weakest performers were the noisier, less structured domains. Finance showed accuracy down to 40% in one model family, and sports was similarly challenging.
Why those?
These are domains driven by sentiment, by microdecisions, unpredictable human behavior, or just fast, non-linear developments that are really difficult to predict just from historical trends.
So they can reason about the structure of a country's fiscal policy, but not whether the S&P 500 will cross a threshold next week.
Exactly right. And what's more, domains like entertainment and technology also proved highly challenging for some models, displaying very high ECE. DeepSeek R1 and GPT 4.1 showed poor calibration there.
Meaning they were often confident when they really shouldn't have been.
Very confident and very wrong. These are areas where trends shift overnight, driven by social media or unexpected consumer adoption, which just breaks historical predictability.
That sets us up perfectly for the central conflict of the research, the news paradox. So after establishing this conditional baseline, the researchers introduced the crucial variable. They augmented the prompt with up to 10 time-bounded news snippets.
Right. They essentially gave the LLMs access to a human forecaster's real-time information edge.
And this is where it gets really interesting. The goal was to see if this additional context would provide the necessary detail to push the predictions up into that 90% accuracy range.
And the result was a genuine double-edged sword.
Okay, tell me first where the news actually helped, confirming our initial assumption.
News augmentation often helped in domains defined by rapidly shifting scope or clarity, or those that were previously hampered by just not enough context. Finance was a big winner.
Really?
Yeah. When news clarified the time frame or the specific context of a financial question, models showed improved accuracy and significantly better Breyer scores.
So if I ask about a bond yield, and I provide the model the latest CPI headline, it focuses its prediction better because it has an immediate, verifiable economic signal.
Correct. Sports also benefited significantly. News is useful there dealing with the short-term team dynamics or, injury reports. For one model family, accuracy in sports jumped impressively from 48% to 64% when news context was added.
That's a massive jump. So news acts as a critical update mechanism in those noisy domains.
It can.
Now, what about the flip side? This is what I want to hear about. Which domains were actively and systematically harmed by the introduction of news?
Here's where the paradox bites the hardest. The very categories that performed relatively well without news context, entertainment, and technology were the categories most consistently harmed by the introduction of extra information.
That is shocking. So, entertainment, which was relying on abstract knowledge about the industry, suddenly crashed when you gave it headlines.
Crash is the right word. When news was added to entertainment questions, DeepSeek R1's accuracy dropped sharply from a decent 68% down to just 40%.
Wow.
And Claude 3.7 saw a significant drop too, falling from 68% to 56%. Technology followed a similar pattern. Even geopolitics, which started so strong, saw a slight but noticeable decline in calibration with the context addition.
So they became less trustworthy in their confidence.
Exactly. So the models performed better when they relied solely on their abstract foundational reasoning about these domains. And the moment you gave them specific real-world headlines, they started failing systematically.
Yeah.
The external information wasn't signal, it was poison.
Poison. That's a strong word.
It is, because the external information introduced highly specific, systematic failure modes, which the researchers identified and categorized as recency bias, rumor overweighting, and definition drift.
And these aren't just random errors.
Not at all. These are systematic vulnerabilities triggered by the very information we assume is helpful.
Okay, let's look at those failure modes with the detailed examples from the source material, because that really helps bring this abstract concept of logic breakdown to life. Let's start with recency bias.
Right. Recency bias is when the models overweight the very latest headline, the most immediate snippet, over the long-term statistical or historical trends that are deeply encoded in their pre-training.
This is a classic human cognitive error, too.
A very common one, but it's actively triggered in the LLMs by this news augmentation.
Give us the finance example they used.
Okay, so the question was a short-term market forecast. S&P 500 above 6050 on June 13. The raw, unaugmented model predicted NO.
And why? What was its reasoning?
It reasoned correctly, based on its pre-training knowledge of market dynamics, mean reversion, the fact that the index was near a resistance point at 6,000, making a sustained breakout unlikely in just 2 trading days. It made a cautious, correct call with about 66% confidence.
A sound, logical argument. So what happened when the news came in?
The news-augmented model flipped its prediction to yes. It read recent snippets describing the S&P flirting with 6,000 and hitting record highs just days before the June 13th deadline.
Uh-oh.
The model allowed those optimistic, immediate headlines to completely dominate its prior knowledge of resistance and market stability. It turned a correct, cautious prediction into an overconfident, wrong bet. Its confidence just flipped dramatically to the wrong side.
So it confused short-term market enthusiasm, amplified by headlines, with genuine long-term structural momentum. It couldn't put the recent information into its proper proportional context.
The crucial distinction it could make. The next failure mode is rumor overweighting. This happens when the model anchors onto speculation, unverified information, or just noise present in the retrieved news snippets. It switches from a correct, cautious stance to an incorrect, overconfident one.
Let's look at the geopolitics example for this one.
Right. The question was a highly sensitive forecast.
Oh.
Tariffs on China above 150% by end of June. The true resolution, as it turned out, was NO. The raw model predicted NO.
And its reasoning was based on that institutional lag you mentioned.
Exactly. It cited policy friction, institutional lag, and the difficulty of quickly implementing extreme tariff hikes due to international law and domestic opposition. Its confidence was high, at 88%.
A sound structural argument. So how did the news disrupt that?
The news-augmented model flipped decisively to yes. And why? Because the context it received included headlines from late April and May that were suggesting that tariffs were likely to rise to 150%.
Ah, suggesting, not stating as fact.
Precisely. These were often speculative reports or, trial balloons floated by unnamed sources. The model overweighted the momentum of the news coverage, the suggestion, rather than the actual institutional process required for implementation, by that strict deadline.
It confused media velocity with actual regulatory velocity. It treated likely to rise as is rising, and it prioritized the most recent speculation over its deep understanding of institutional inertia.
Exactly. And this shows the peril of feeding high-stakes speculation into a model that isn't robustly trained to discern source credibility or the difference between a political rumor and enacted policy.
The final systematic failure, definition drift, is maybe the most concerning because it suggests that augmenting the prompt fundamentally shifts the model's internal understanding of the terms themselves.
This is semantic shifting in real time. It's when additional news shifts the model's semantic grounding, causing it to misinterpret acronyms, industry context, or even temporal cues.
Take us through the technology example involving the acronym MES.
Okay, the question was, will Matt's applications open in March? The true answer was yes. The raw model predicted yes.
And it knew what MATS was.
It correctly interpreted MATS as a recurring academic program that historically opens applications in March. It used its core knowledge about academic timelines and
It's
context.
perfect sense. It correctly identified the domain.
But the news-augmented model predicted NO. And the reason why is because the news snippets it retrieved were heavily dominated by references to the Mid-America Trucking Show, which also uses the acronym MATS.
Oh no.
And since trade show registrations opened months before March, the model shifted its entire reference domain. It ignored the contextual cue about applications and substituted this new, dominant meaning provided by the news. It led to a confident, yet entirely incorrect prediction.
That is profound. It's choosing the most search-visible meaning, the headline context, over the contextual fit of the original question. That means the news didn't just confuse the model, the news fundamentally broke its reliable internal knowledge base and semantic boundaries.
It illustrates that the models are highly sensitive to contextual framing. If you provide specific anchors, even if they are factually correct news items, the model may drift away from the central meaning of your question.
It's also worth noting one final quirk the researchers observed with one of the models, DeepSeek R1.
Yes.
It sometimes failed to provide its required reasoning traces, even when explicitly prompted to verbalize its process. The result tags were there, but the rationale was just missing.
And that just underscores a lingering concern. Even with these structured, rigorous prompts designed to elicit transparent reasoning, the process isn't always reliable or visible. And that is incredibly worrying when these models are tasked with high-stakes financial or geopolitical forecasting.
So what does this all mean for you, the listener, who is likely using AI tools right now for analysis or prediction? What's the ultimate takeaway from all this?
The study shows pretty clearly that an LLM's future reasoning ability is conditional, not emergent. Their predictive accuracy depends entirely on what and how we ask, and whether the external context we provide is helpful signal or, well, dangerous noise.
So the practical application here is critical.
Yeah.
If you are using generative AI for analysis or prediction, you have to be extremely cautious about how you integrate recent, uncurated information. Simply appending a stack of recent news snippets can activate these specific biases, definition drift, rumor overweighting, recency bias.
And that can turn a correct, cautious baseline prediction into an overconfident, spectacularly incorrect one. You have to curate your context, not just augment it.
That's a huge distinction.
And if we connect this to the bigger picture, the current approach to evaluating LLMs often focuses heavily on standardized tests measuring knowledge recall and immediate reasoning. This research raises a really important question.
Which is,
Given the profound and systematic nature of these failure modes when external context is introduced, how can we design future LLM benchmarks that successfully disentangle a model's existing reliable knowledge from its true ability to perform robust probabilistic inference?
so we need tests that can tell the difference.
We need tests that reward models for understanding when to trust their abstract structural knowledge and when to incorporate new context without breaking their semantic grounding.
That is a challenge that moves us beyond simple accuracy and into the realm of true reliability, a necessary step for AI in the real world. A great provocative thought for us to consider as we watch these models evolve.